Okay, good afternoon. Hope you're enjoying the snow. All right, so we finished our discussion for now for the integer quantum Hall effect. And naturally, we want to go to the fractional quantum Hall effect now and other related topological phases. But before we get there, we need to develop certain technology. And this is the technology of Berry curvature, Chern numbers, and Chern-Simons gauge theories, and which will be the topic for the next 2 or 3 lectures before we apply everything we have learned together to understand the fractional quantum Hall effect in its most general setting. Anyway, are there any questions about what we've covered so far on the integer quantum Hall effect and related topics? Okay, so I'm going to begin with a fairly general discussion about Berry phases and how that connects to topology. My treatment is actually drawn from mostly from the book by Gerwin and Yang, which is, I have a copy here, Modern Condensed Matter Physics, which has a nice discussion of these topics. Okay, so the idea is you have some Hamiltonian H, which depends on parameters. So these are just some classical parameters, could be the pressure, the density, chemical potential, location of quasi-particles, momentum, whatever. There's just some set of parameters that you can tune in the lab. So there's some parameter space, which will usually be multidimensional, mostly interested in 2 or higher dimension in the parameter space. And for every point in parameter space, you have a different Hamiltonian and therefore also a different set of exact eigenstates. So here we assume psi n of r are just the set of all eigenstates of H of r. Okay, so this is a map then from parameter to space to Hilbert space. So we really have then a set of Hilbert spaces. It's not just one Hilbert space. Each R gives you one Hilbert space, where we have a whole set of them associated with every point in this parameter space. And this whole parameter space of Hilbert spaces has a certain important geometric characteristic, which we'll now describe, called the Berry curvature. Any such parameter space has a Berry curvature. Often it's just 0, but sometimes it's not. And when it's not, it can lead to some very interesting effects, which is what we're going to talk about. Okay, and then like I mentioned last time, this Berry curvature and the Berry connection, although they appear in the description of the adiabatic process, they're really kind of independent of it. And they just properties of geometric properties or topological properties of Hilbert space that are very useful. But they appear most naturally in the adiabatic context. So let's consider the adiabatic process. So you have this parameter space R, and let's imagine the parameters R vary slowly with time. So now instead of thinking of a Hamiltonian as a function of the parameters, it's a function of time. H is a function of R, which is then a function of time. R is a vector, it's not a scalar. So this is your Schrodinger equation that you want to solve. So now, of course, it's not easy to solve this. It's a time-dependent Hamiltonian. We can't solve it in general, but you can solve it almost completely for the case where this variation in time is very slow. So to solve this, which is called the adiabatic variation. So to solve it, what you do is you find the eigenstates, which are labeled by little n of r, for each r. So you have this whole parameter space, you diagonalize it, and you get n of r, which over here I call psi n of r. Sorry about that. So this is nothing but the same thing. So this is equal to n of r. Okay. So you determine all of the n of r and the epsilon n of r. And a key observation that will play a central role is that there's a phase here. You can always choose the phase of n of r to be different. It's up to you. It doesn't affect the eigenstate. So just saying that you determine h of r is fully fixed, but n of r is fixed only up to a phase, and it's up to you to choose what that phase is. And because of that, for many years, people kind of ignored this phase because it seemed like, well, you can choose it, so why should we worry about it? It's nothing. It's just a convention. Well, that's true up to a point, and that's where we want to get to. All right, so you've diagnosed for every r, and now you want to go back and solve this equation. All right, so now the adiabatic theorem tells us that if the variation is slow, and if you start out at t equals 0 in some eigenstate, so psi of 0 is n of r of 0, then you will remain in that eigenstate if the variation is slow enough. That is, as you vary the parameter r, you will remain in exactly the same state. So you've got some set of levels which are varying as a function of time. There's one level here, another level there, another level there. So this is some energy level, and this is time. So you start out in one of these levels over here, and you move, and now it could happen as you move in time that you undergo a transition, and part of you is here and part of you is over there. You could mix with the other state. But that happens very rarely. There's something called the Landau zero tunneling probability of when that happens. And in fact, that probability goes to 0 quite rapidly as the rate at which you're varying goes to 0. So we assume we are varying slowly enough so that we just remain on the same eigenstate. And of course, how slowly? Well, it's slowly, the rate should be smaller than the energy gap. So whenever two levels really come close to each other, then you have to be extra careful there to avoid jumping into the other level. So we assume that's the case, that the levels remain non-degenerate and separate, and you're varying slowly enough that you never make a transition. So in that case, psi of t is some phase factor times n of r of t. Okay, so now this is a very general statement, but now let me write a specific form for Cn of t. It's a phase factor, which is the integral of the instantaneous eigenvalue. So En of t is just En of r of t. So the instantaneous eigenvalue, which you integrate, times an additional phase, which is of course what we are really interested in, is gamma n of t. So this is this is just the ordinary phase that you pick up when you're integrating Schrödinger's equation, and gamma n is the phase that you care about. All right. Now, as I just said a moment ago, the phase of these eigenstates is completely up to you. So we could have always taken this n of r and t and redefined it by some zeta of t. And zeta of t can be any function I want. Well, if you redefine it this way, and it would appear that gamma of t is not well defined. Okay. Well, so how will gamma of t change if you make this change? So let's just figure it out. So first, let's determine what gamma n of t is. Okay, so you take this ansatz, which you have here, and you plug it back into the Schrödinger equation, which is here, the time-dependent Schrödinger equation, and just take the time derivative of everything. Then what you'll find, so there's a couple of steps I skipped here. When you take the derivative of this, you'll pull down a factor of epsilon n, and that will precisely cancel the fact that h acting on psi gives you a factor of epsilon n. So this is just this is there just to make sure everything just all the usual factors just cancel out related to the Hamiltonian and the energies. But then there's another term from d gamma n dt that we have to keep, and that will appear. Well, okay. Yeah, so there's a term from d gamma n dt, and there's also a term on the left-hand side from dn dt. So dn dt is just the rate of change of whatever you call n of r of t to be. Okay, you keep track of those terms, and you take the inner product with n of r of t, which is a normalized state, and then you get this very important result here, that d gamma dt is is this quantity right here, which is n d by dt n. And if these states are normalized, this right-hand side is a real number, or this matrix element is purely imaginary. It's easy to show. Let me see here. Well, I'll show these things. Yeah, so yeah, I guess I show it here. Just wait a minute, I'll show that that's real in a minute. So this thing, I can now lose the chain rule and write it as an integral over R, over parameter space, rather than over time. And then you get this A, so this vector A, this is a vector in parameter space now. You want to get rid of the time dependence as much as you can and refer everything to parameter space, dotted into dr. And this A is then the R derivative of n of R. Okay. So this is what's called the Berry connection, A of R. It has nothing to do with, no reference to any time variation. It's just a quantity which is, in fact, behaves very much like a vector potential, but it's a vector potential in parameter space, because the vector here refers to the vector here, which is the space here. So on this space then, on this parameter space, you've defined a set of vectors at every point in space, and that's the vector potential, the Berry connection. Ordinary vector potential is a vector in real space. This is a vector in, very much like the vector in parameter space. So now comes the point: why do we think it's like a vector potential? Well, if you do this this transformation, if I chosen different phases here in the definition of n of r, and I can write zeta as a function of r or t, it doesn't matter. Then if you make that change and you plug that in here, so you plug in n goes to e to the I zeta times n, and plug it in here, then you find that A will change. And how does it change? Well, exactly like any self-respecting vector potential, it changes at the gradient of the zeta, which is the gauge transformation. So, so there is this Berry connection, which is a vector potential in parameter space, which is not gauge invariant because it changes with gauges. But now we know, of course, yeah, well, then there's an electromagnetic field which is gauge invariant, and that electromagnetic field is what's called the Berry curvature. So there's the analog of the electromagnetic field in real space is the Berry curvature in parameter space. Okay, so here's just a math interlude for various things we kind of assumed. So here I'm using short. This is the same as n of r d by dr mu of n of r. So I just rewrite that in short form as n d mu n. Occasionally we'll have to take a derivative of the bra rather than the ket on the left and the right. Then you have to play with the notation a little bit to put an arrow or something to make sure it tells you which direction this d mu is acting. Or equivalently, you do what's done here. Okay, I'll explain that in a minute. So this is the Berry connection. Now mu refers to components in parameter space, not real space, but it's very similar, obviously. So So it's normalized to unity, and I take a derivative. And now what this thing is referring to is this quantity here is the same as n of r d by dr mu, but acting on the left on that side times n of r. Okay. So this is a nice way to write it. So you get a derivative of the bra and the cat. They have to sum up to 0, and also, well, this is obviously the complex conjugate of that. So this tells you A mu is real. Okay. So you can also write A mu in this way. You can just use this equation and write it explicitly so that it's real, so that this is just the complex conjugate of that. And now let's work out the Berry curvature, which is the gauge potential. So that's the F mu nu here. This is the Berry curvature. Just work it out with the chain rule, and sometimes this term with two derivatives cancels with that, and this is it. So this is the answer. It's d mu n overlap d nu n minus d nu n d nu n. So that's the very important result here, and here's stated or written out more explicitly. The Berry phase itself is a gauge is. Oh, yeah. So now the another way to say this is to say that the gamma n that I wrote down here is not a gauge invariant quantity, gamma n being the line integral of the vector potential. It's not a gauge invariant quantity. But suppose I take a closed loop in parameter space. So what I'm going to do is, here's my parameter space. This is my parameter space here. This is the space R. And I take a closed loop in parameter space. So if I took a closed loop in parameter space, come back to the original point, so that my Hamiltonian has returned to its original point, then this is gauge invariant. This is a pure number that characterizes the structure of your Hilbert space. It's just because it's gauge invariant. Okay. And now, by the usual trick, the line integral of A on any surface like this is it must relate to flux by Stokes theorem, and so it's the integral over the surface. This is the more fancy way of writing that, times this quantity, which is then the Berry curvature. Notice the Berry curvature depends on n, which is which state you're referring to. So every state here that I drew here as a function of the parameters, every state has its own vector potential and its own Berry curvature in this parameter space. Okay, so there's the quantity that I already given. All right, so I've given you then in principle a prescription to compute this, which is rather tedious though. What it says is that you pick a set of states over all of, make a gauge choice. And once you made the gauge choice, you compute A(n) of r. And then after you've computed A from this, you compute its curvature, or more explicitly, it's given here. Well, okay, sorry, more explicitly, it's here. Okay, so that if you want, let me write it out in its full glory. That's I times, dn by dr mu times dn by dr mu minus the opposite. Okay. Now, often when you're dealing with problems, this is kind of difficult to implement, especially on a computer, because you have to make sure that your n of r has a unique phase choice everywhere in parameter space. And if you're determining n of r by diagonalizing some matrix in Mathematica, well, mathematically it just gives you an eigenvector with some random phase choice. So you have to make sure that it's giving you sensible phase choices that are consistent, and then compute the query curvature. But so it seems like the final answer should be gauge invariant for your phase choice, as long as it's single valued everywhere. But it's a little tricky to make it work out from this definition. However, you can play a few tricks and get an expression which is written here, which I'll write down again. You can relate the derivative of these kind of matrix elements that you obtain over here, these kind of matrix elements, or even in A mu. A mu. Oops, what happened there? Okay. Okay, that's fine. You can relate the mu here, the matrix elements that appear here, to derivatives of the Hamiltonian. And derivatives of the Hamiltonian are much nicer than derivatives of states, because the Hamiltonian is not arbitrary. So that's the trick you use. So you take the defining equation for the states, take a derivative of the left and the right-hand side. And so then this relates n prime d mu n, the kind of thing that appears in the vector potential, to just a matrix element of the derivative of the Hamiltonian. Okay, so you do that kind of algebra. It's a bit tedious, but not difficult. And then you get an expression, which I will try to write down again, for the Berry curvature. So the Berry curvature of the nth state, and the mu nu components of it, like f mu nu. So it depends on which point you're in parameter space, is equal to I times sum on n prime not equal to n. And then you have a numerator, which are matrix elements of the derivative of the Hamiltonian, which is what we love, because they're easy to evaluate. N dh by d r mu n prime minus interchange mu with mu, the whole thing, divided by En minus En prime whole square. So there's our grand expression that we're going to now employ and apply to many problems. Okay, so a very general discussion. As long as there's no degeneracies in your eigenstates, pick a Hamiltonian, which depends on R, find all its eigenstates, then take the derivatives of the Hamiltonian and take the matrix elements between your eigenstates. And now you notice this is explicitly gauge invariant. If I change the phase of n prime, the phase over here will cancel with the phase over there. And similarly, the phase of n will cancel the phase of n there. So now you can easily put this on your computer. It doesn't matter what eigenstates your Mathematica spits out. The answer won't depend on the phase. So you just need the derivative of the Hamiltonians, which explicitly are gauge invariant, not up to you. You're given the Hamiltonian. And then you compute this. And so this is the exact expression for the Berry curvature of any Hamiltonian with a non-degenerate spectrum as a function of some R's. Okay, very general and very important result. Okay, and also, this smells like perturbation theory. If you look at these expressions, these are the kind of things you see in perturbation theory. So you have matrix element in the numerator and a bunch of energy denominators. But this is not perturbation theory. This is the exact answer, the full answer for the Berry curvature at any point in parameter space for any Hamiltonian. Okay, so you just have to, now it's up to you to evaluate the sum. Yeah, and this thing never vanishes as long as there's no degeneracy. So this fails completely when and two levels actually cross. So you want to avoid, you choose your parameter space so you avoid that region. Any questions? Charge my other computer. Okay, so everyone's with me here now. All right, so now we've got the Berry curvature. Let's just apply this formula in lots of cases. Okay, so the most important problem, the first problem which Berry himself applied it to, is just a qubit. Okay, so or a spin and a half, depending on your taste. So your Hamiltonian is extremely simple. It's just h dot sigma, and h is a unit vector. Okay, so of course, if it wasn't unit, you'd have to rescale it out. And our parameter space is just theta and phi, the angles theta and phi. Of course, this is not doesn't have this topology of a torus. It has the topology of a sphere, and you have to, of course, keep track of that. But this is what I'm just drawing, just to emphasize the point that this is a parameter space. I should really draw a sphere, but it's because of my limited drawing ability, I'm just drawing a rectangle. So theta and phi are parameters that are going to vary as a function of time, if I wish, but really it's just I want to know something about the structure of this Hamiltonian as a function of theta and phi. And I know the eigenvalues. The eigenvalues are actually independent of theta and phi. That's even simpler. The eigenvalues of there's two states, and the eigenvalues are just equal to plus or minus h. They're independent of theta and phi. So as I rotate the field, I just get two levels separated by theta and phi. So they never touch, or they never cross each other. If I want to think of a three-dimensional parameter space, then what I'm doing is I'm moving on the surface of a sphere in 3 dimensions, and there's a degeneracy or singularity at the center of the sphere, where the two levels become, where the vector h is 0, and that's where the two states become degenerate. So we split the degeneracy, and we're looking at the topology of the space around the degeneracy point at the center of the sphere. And as we'll see that now our parameter space is a sphere, and the Berry curvature is just like the magnetic field of a monopole at the center of the sphere. Okay, the Berry curvature should be spherically symmetric, because it's gauge invariant. All right, so if you just explicitly want to do the calculation, you take the minus eigenstate, and you can check that this is an eigenstate of capital H. So this is something that is gauge dependent. You could have put an extra factor of e to the phi outside, and so on and so forth. And then you compute the vector potentials in the theta and the phi directions by the usual rules. And if you work it out, this is what you get. And then finally, the Berry curvature. So here I'm doing it the first way, where I actually compute the vector potential. I'm not using this general expression. You could do it that way too, but either way. So if you then compute the Berry curvature, that gives you 1/2 sine theta. Okay, so now you have to integrate this over the parameter space. And for Stokes' theorem to apply properly, you have to, well, what is it? I've forgotten how it all works. That's where these differential forms come in. Somebody tell me how this works. No, you just integrate over theta and phi. That's correct. So if you integrate this quantity over some closed curve, sine theta, d theta, d phi, well, that is nothing but the solid angle, or the area enclosed by the curve, times a factor of 1/2. So that tells you that the Berry phase, if I take a spin and I move it on this path and have it come back, it picks up a Berry phase, which is the 1/2 times the area enclosed by the path. So that's the famous Berry. It should be called the Berry Pancharatnam phase, because Pancharatnam also worked it out for this case earlier in a different context, though. All right, so that's the Berry phase for a spin enclosing any path on the surface of a sphere. Yeah, so here's the gamma, which is the integral of d theta d phi, which is nothing but the area enclosed by the path. Okay. You can also do this for a spin. No, not this is a spin 1/2. You can do it for spin 1, spin s. So the calculation is more complicated because then you have 2s plus 1 states. But then you find that the Berry the Berry phase that you pick up is s times omega, not 1/2 times omega, but s times omega. Also, another nice thing you can see here is that the area of, if you have a path on the sphere, the area, you can either think of this as area omega, which is here, or the area outside, which has the opposite sign. And that area would be omega minus 4 pi. Okay, so because you're going clockwise rather than anti-clockwise around it. So around here, the area of the other side is minus of 4 pi minus omega. And which area is the right one? Well, the answer is either one. They're both valid from this way of thinking. And it doesn't matter which one you pick, because e to the I, the 4 pi doesn't change anything. E to the is times 4 pi, if I did it for spin s, is always equal to 1. And so this shows you, in fact, this is the world's most complicated way, well, but very elegant of seeing that spin has to be quantized in integer or half integer. Because if it wasn't, this Berry phase wouldn't be defined. So you can take either area, you get the same answer. All right, so that's the most famous Berry phase, where the Berry curvature, as we saw in the right units, is just if I take a little curve like this, the Berry curvature of that is just the area. So it's basically uniform. It's just a vector pointing vertically outwards in the right units, and the Berry curvature is the same everywhere. And so that's like a magnetic field pointing radially outwards, completely uniform, with a monopole, in this case of strength S or strength 1/2 at the center of the sphere. So the Berry curvature of a spin 1/2 in this angle, in this space of the orientation of the spin, is similar to the physical magnetic field of a magnetic monopole. All right, questions on that? Okay, then let's get to where we really wanted to get to. Let's apply this to block bands. Okay. So hopefully you know a little bit of solid state physics. The Bloch's theorem tells us that if you have a periodic potential, then the eigenstates, the one particle eigenstates of a periodic potential, the psi k, are labeled by what's called the crystal momentum k, which lives in the Brillouin zone, and a function u for each band n, which is periodic. So u and k of r plus any primitive lattice spacing gives you back the same function. So this is a periodic function here, the u. Okay. And if you start with the original Hamiltonian, then the equation determining un of k It's just the Schrodinger equation here. H times U is epsilon times U. And because you shifted the momentum by K, H of K has an extra K in here. Okay. So this is the periodic potential. I also added an external magnetic field if you wanted to. P is, of course, always H bar over I grad. So normally, if you didn't, if you just consider solving some arbitrary problem, this would be the Hamiltonian without the H bar K. And what the Bloch's theorem tells you is that you get a whole bunch of eigenstates, which are not exactly periodic, at the cost of having a slightly different Hamiltonian. So basically, you have a different Hamiltonian at every point in the Brillouin zone. So that's the key picture here to keep in mind, where you can now start applying the theorems about Berry curvature. So here's our Brillouin zone. So if I take a square lattice, which is usually the simplest and most important case. So here's my momentum space for a square lattice. So this is Kx. Let's say it goes from 0 to 2 pi over the lattice spacing in the x direction. And the momentum here goes to 2 pi over b. So this is a lattice in real space where this spacing is a and this spacing is b. And if you want to take other complicated lattices, then you have to take a course on solid-state physics. But this is the simplest case. So the square lattice, you're simply just taking Fourier transform. And your wave function then, psi, is labeled by a wave vector k and a function of r. And it's equal to e to the I kx times x plus ky times y times a function I'll call u, which also depends on k of r. And this u obeys the conditions uk of r plus a equals uk of r plus b in the y direction is just uk of r. So this is the content of Bloch's theorem, that every eigenstates of the Hamiltonian with a periodic potential can be written in this way. It's some plane wave times a periodic function. So at every point this is now our parameter space, kx and ky. At every point in parameter space, I have a Hamiltonian h of k. So k will become like r. And I have a state for every point, which I'll call u sub n of k. In fact, I have a whole set of states. These are the bands. And so at every point in parameter space, I have this state. And now all I have to do is just determine the Berry curvature of every band. So every n will have its own Berry curvature, which will depend on the k. And now my parameter space is this, and that's going to be important in a minute, because this line here is the same as that line there. And similarly, this line here is the same as that line there. So that periodicity is going to be crucial. So now my parameter space is torus, and I have a set of some Hamiltonian h of k, which is completely general. And I diagonalize it for each k. I get a set of states, un of k, n is the band index. And now I just go ahead and compute the Berry curvature. Okay, so now this is, I haven't told you what h of k is, so I can't do anything more other than just go ahead and apply the various formulae that I've written down. Okay, so the Berry curvature, if I'm in 2 dimensions, the Berry curvature will be just a scalar, because there's only one magnetic field in 2 dimensions. If you have x and y, then there's only the b field in the z direction. And we limit ourselves to that case. In higher dimensions, if I have 3 dimensions, then the Berry curvature is a vector. And this is the general form of it. It's the cross product of the derivative of un of k with itself. So what we're doing here is implicitly, here I wrote down the Berry curvature as two indices, but if I'm in 3 dimensions, I can think of the Berry curvature as a vector. Mu is just 1/2 epsilon mu nu lambda of omega nu lambda. So in 3 dimensions is a special case where I can replace a second rank anti-symmetric tensor by a vector, axial vector. Either is good enough, as you do in electromagnetism. And in 2 dimensions, you can replace it by a scalar. There's only one magnetic field, which is omega xy. Okay, so that's the expression for it. And initially, when you look at this, that's got to be 0, but it's not, because this is a complex number. And you have to take the real and imaginary parts, and then you can get a non-zero value of a complex vector with itself. Okay. But I had also given you this very general expression for the Berry curvature independently of which is gauge invariant explicitly. And here it is. I mean, I'm just rewriting the formula I wrote earlier for the Berry curvature. Here, you just have to take all the bands at each k, and then just do the sum. Take this cross product, and you'll get the Berry curvature. Or in 2 dimensions, life is even simpler. The Berry curvature is a scalar, but it depends on 2 momenta. And you have to take the derivative of respect to kx and ky minus ky over kx and divide by this. Okay. So it seems like, we are floating somewhere in some very complicated set of formulae, which have neither rhyme nor reason. And there it is, the expression for the Berry curvature of some band. And in fact, you can see that if the wave function can all be chosen real, this Berry curvature is 0. So to have any Berry curvature, you need to have some broken time reversal symmetry, either in a ferromagnet or in or due to an applied magnetic field, and so on. But it's some numbers that you'll get that at every point on the torus, which is the Brillouin zone. Okay, so now comes the surprising result, which was first proven by Thouless and the famous TKKN paper. Thouless, Komoto, sorry, I forget the names, and Nightingale was the last person. Or TKNN, was it? I don't know. Okay, well, apologies to the others, but Thouless is the one who got the Nobel Prize, presumably because he was the lead author. What Thouless noted, that this expression for the Berry curvature has a very close connection to the Hall conductivity. So this is the connection to the previous lecture, really. And in fact, there's a certain property of the Berry curvature which then shows that the Hall conductivity is quantized in 2 dimensions. Okay, so before I get to that connection, let's actually see the quantization in action. Now we saw a version of this here also when our parameter space was a sphere, surface of a sphere, and the Berry curvature was just the area extended by the sphere. So if you now took the integral of the Berry curvature of the entire sphere, you had to get 2 pi for spin a half, or 2 pi s for a general spin s. Okay, so we can try to do a similar thing here. Now we don't take the integral over the sphere, but we're going to take the integral over this torus over here. So we take our Berry curvature, which has many different definitions, and we're going to integrate it over all kx and ky, and because because of the way things work out, we're not putting the factor of 4 pi squared as you normally would if you were integrating over the Brillouin zone. We put a factor of 1 over 2 pi. And this integral was something that had appeared in mathematics. It turns out to be something called the Chern number of these functions on a torus. Okay, so what is this integral? So here's our Brillouin zone again, and I want to take the integral of the Berry curvature, which is some function of kx and ky over the entire torus. So by Stokes' theorem, that's the line integral of the Berry connection on the boundary of the torus. Okay. Here I'm taking the torus to be just exactly this strip here, from 0 to 2 pi. Okay, and so that I know what the Berry connection is. It's just it's as I wrote it earlier. Previously I'd written it as n d mu n. This is exactly that formula, but now d mu is replaced by dk, and I've written it out as an explicit integral. Integral over dk. All right, so what is that? Well, now if you think about it a little bit, first of all, it doesn't look like anything. Then you think about it a bit more, then you say, oh, it must be 0. And then you think about it more carefully and realize, no, it's not exactly 0. So step 1 would be, okay, so I'm taking the integral along this boundary of the Brillouin zone shown here in this purple curve. So the functions are periodic. So we know that this momentum, for example, Ka is the same as the momentum Kb, because they differ by exactly 2 pi. So they will give you exact, those exactly the same periodic functions, uk of r. So you will say, okay, well, then I have this integral on this line here and that integral on that line here. They cancel, and therefore this is 0. Okay, that's a little hasty, because first of all, you have to choose something, choose uk of r everywhere in the Brillouin zone. You have to choose it from not only at point A and point B, you have to choose it all the way from here to there in some smooth, continuous way for this thing to make sense. And it may be that there's no gate choice where they become exactly the same. So the point is that the UK that you pick over here and the UK that you pick over there, they're eigenstates of the same Hamiltonian. They obey the same equation that determine the fact of the UK over here and there. But just because they're eigenstates of the same Hamiltonian doesn't mean they have to be the same. They can differ by a phase. Okay. So what we can say very generally, so this is the statement written out more explicitly. So UK of r is a periodic function, so it can be written as some numbers times e to the I, so like any Fourier series. This is just the Fourier series for a general lattice. For the square lattice, it's literally the Fourier series. And the Hamiltonian just gives you a set of matrix equations for the CG. And it's the same because at this point and at this point, because those two differ by a g, so all you're doing is just rearranging the coefficient CG. So you're not really getting a different Hamiltonian or a different eigenstate. Okay, so they're both, so the CG are obtained by diagonalizing the same matrix at Ka and Kb. So, but they don't have to be equal. So they can be an arbitrary phase, e to the I theta of K, that they differ by. That is, if you try to make a solution here and smoothly continue to the other point, you won't end back to the same solution. You'll end up the same solution up to a phase. Okay, so now I use this equation with some unknown phase theta of K, and now I do the integral. So when I take the derivative, I get two contributions. I get the contribution from the gradient This is the gradient with respect to k. So I'll get the contribution from the gradient of theta, and I'll get contribution from this. Now the contribution from this will certainly cancel against b because they're the same function up to this phase. So the only thing that's left over is the phase. So consequently, the integral of the Berry curvature, which is the integral of the Berry connection along the boundary, is just the integral of the gradient of this phase. And this phase is single valued, but it could have gradients. So when it comes back to itself, it can differ by an integer multiple of 2 pi. And that's why we put the 1 over 2 pi here. That's the mathematical convention. And this integer is called the Chern number. So what we learned is that any band in solid state physics in 2 dimensions, you take any crystal whatsoever, with any band whatsoever, that whole band is characterized by a number, an integer, which is the Chern number. Now, in almost all the bands we've met so far, in fact, all of them, it's just 0 because you can always choose a phase so that it's just constant. It's the same everywhere, and you're done. But you do get bands which have non-zero Chern number. And in fact, that's the way to think about the Landau level. If you take, a periodic potential and a magnetic field, and you slowly send the periodic potential to 0, you get the Landau levels. Well, the Landau levels are basically the remnants of the bands which had a non-zero Chern number. So that's really the more important property of a Landau level, the key property, that is, it's like a band with a Chern number, but it was kind of a degenerate case where there was no dependence on position or momentum. And so that property was kind of hidden. But once you add a periodic potential, this becomes quite evident. So that's the Chern number. It's the integral of the Berry curvature of the band in 2 dimensions over the Brillouin zone. Okay. How are we doing on time? All right, so this is, I guess, yeah, let's talk about this. So now of course, we want to compute this everything. It's not easy. You have to, I think if you wanted to actually compute the Chern number, we've proven it's an integer. But to actually compute it, we would have to go back and put this whole mess on a computer and integrate it over the Brillouin zone. And in fact, I wrote some mathematical programs to do it, and it's really exciting when you do the integral and it comes out to be an integer. So maybe, yeah, I think I might share those programs, or I'll put them in a homework or something. Yeah, and it does work, I can assure you. I checked it. Okay, so we've said that each band of a 2-dimensional crystal is characterized by a topological invariant. So this is topology in a different sense than the topology we met when we talked about anyons and the phases of the anyons. This is a band topology. So there's and unfortunately, the literature uses the word topology interchangeably between two very different ways of thinking about it and two very different contexts, but nothing you can do about that now. Okay. So there's a topological invariant that characterizes every band, the Chern number. And as I've already said, it's usually 0. And why am I calling it a topological invariant? The reason it's an invariant is that because it's an integer, it can't change. Suppose you give me a Hamiltonian with some bands, and then you start changing the Hamiltonian a little bit. But if you change the Hamiltonian a little bit, it can't possibly change the integer because the integer has to be an integer. It can't jump for a small change in the Hamiltonian. And by making a series of small changes, you can make a big change. So even for a big change, you conclude that this integer doesn't change. So that's why it's called a topological invariant. Because it doesn't really depend upon the Berry curvature is not a topological invariant. The Chern number is is a Berry curvature depends on the every last detail of your Hamiltonian. But the integral of the Berry curvature, or the Chern number, is a topological invariant. So how can C change? Well, you can. So in fact, the main assumption in the derivation was that there was always a gap. So if you have two bands, say one band with Chern number 1 and another band with Chern number 0, then they have to meet at this point somewhere in momentum space and then separate again. And it's only this process that can lead to a change in the Chern number. And right at this point, you can show quite generically that the dispersion is that of a massless Dirac fermion. So it's only at these Dirac points that the Chern number, when that appears in your parameter space, for some reason, two bands kiss at a Dirac point and then separate, well, then the Chern number can change. And it basically jumps from one to the other. If one Dirac point intersects, this Chern number goes down and this one goes up. So the delta C on both sides is plus or minus 1 for one Dirac point. And then you can see if you want to have a bigger change, you've got to have multiple Dirac points intersecting at the same time. Then you can have bigger jumps. Okay. And finally, I guess this time we haven't established this, but what we will see is that this Chern number is intimately connected to the Hall conductivity, and this means that just like as we found for Landau levels, by the same anomaly inflow argument, you realize that if you have a crystal with a non-zero Chern number, then at the edge of the crystal there must be edge states, which are protected topologically as long as the Chern number is non-zero. So that's another important property of this Chern number. It implies protected edge states. Okay. So the last step in this argument, from which everything then follows, is this, which I will prove next time. That if you have a crystal, any crystal, and you apply magnetic field to it, and then it's an insulator. That's the same. So the chemical potential is between the bands. So it's an insulating crystal in 2 dimensions. And then its Hall conductivity is given by this. It's E squared over H times an integer. And that integer is just the sum of the Chern numbers of the field band. So this is very similar to the integer quantum Hall effect, where it's E squared over H times an integer, where integer was the number of filled Landau levels. So here, for each Landau level, you got E squared over H. Here, for every band, you get a Chern number, which can be not necessarily 1. It could be 2, 5, minus 3. It can be rather much more complicated, and depend in detail on the periodic potential. Okay, I think I'll stop there. Any questions?
Yeah, I had a question about the gap closing thing that you showed just before.
Yeah.
Is it just an accident that the sum of the Chern numbers is like 1 on both sides, or is there some like conservation of total Chern number?
Well, you can explicitly work out quite amazingly what happens when you have just one Dirac fermion. If your bands meet at just one point in momentum space, so you have just one Dirac fermion, then you can show that the change in Chern number of both bands has to be plus minus 1. So if this goes from 0 to 1, that'll go from 1 to 0. So if this is plus 1, the bottom will be minus 1. And that depends on the chirality of this Dirac node, which way it goes. But it can't, in other words, each Dirac node like this is like a flow of just exactly one Chern number. The total sum of the Chern numbers is preserved. In fact, the sum of the Chern numbers of any crystal has to be 0 if you sum over all bands. But what happens is the sum of the two is the same. I mean, it could, in principle, have gone for an opposite chirality Dirac closing. This could have gone, for example, another possibility that could have happened if this could become C of minus 1, and this becomes C of 2. So this one increases and the other one decreases. That could also have happened. And that depends in detail on the structure of the Dirac node. But that's the only possibility. Dirac nodes can only do a delta C of 1 for both the bands. And the sum of the, in this case, the sum of the C's is still 1. 2n minus 1 is the same as 1 plus 0. That's really the only thing that happens. Now, sometimes you can have, at different points in the Brillouin zone, two Dirac nodes touch at the same point, like in graphene. Both Dirac nodes are present at the same point, at the same time for the same set of couplings. And if that happens, then the delta C can be 2, and so
on. I see. Thanks.
So that's a calculation. You can show that. So what happens if it's very tedious, but it turns out that the Chern number near the Dirac point is just given by the vicinity of the point. So you don't even have to worry about very large momenta. You can just do the integral in this region. So if you just apply, if you take a Dirac dispersion and have the Dirac mass go through 0, and just apply this tedious formula here, you will verify the statements I just made. There's an easier way to do it using the Cooper formula. Once I use the Hall conductivity as a stand-in for the Chern number, but in principle, these statements that I made here can be verified by the formula I've given you. Okay.
Hi, I have a question. We're calling A the connection. Is there some sensible covariant derivative that we can define with that A?
Not sure. Good connection.
Like some kind of covariant derivative on the parameter space.
Yeah. I mean, I think if you look at the equation of motion, yeah, I mean, I think if you make, so what happens, and that's the way it often appears, in fact. So right now, the parameter space was just a set of fixed parameters. But now imagine that the parameter space itself it becomes dynamical. I mean, this is kind of in the Born-Oppenheimer picture. So when you talk about, say, a molecule, you think of the molecule as made up of the position of two nuclei, and you solve for all the electrons. But then you allow for the nuclei themselves to move. So at that point, the position of the nuclei is your parameter space. But then you look at vibrations of the molecule. Then and it's a good approximation to think of the parameter space. The electronic states are just determined from the instantaneous eigenstates of the nuclei. So if you now write down a theory for where the parameters themselves become dynamical, like the positions of the nuclei in a molecule, then you will get a covariant derivative in terms of those potentials. So then the Berry connection will be the connection that will appear in form of covariant derivative with respect to gradients of your parameter space. Okay, so, or in our case, when we talk about quasi-particles, we always say, well, localize the quasi-particles and move one around the other, and you get some anionic phase. Well, I mean, in the end, but the anyons are not really localized. They obey some Hamiltonian. So if I want to write down a Hamiltonian for the anyons, I'll have to write down some kinetic energy for the anyons, and in the kinetic energy for the anyons will have involved covariant gradients involving this Berry connection. Yeah, so a good question, yes.
I see. Very cool.
Yeah.
Thank you.
Sure. Okay, so I'm supposed to meet with at least two of you now on your course presentations. I think almost everyone is up there on the website. We really have a lot of, it's going to be fun listening to all of this. I'm sure I'm going to learn a lot, but it's going to take some energy. But But anyway, so okay, thanks. And then those of you who want to discuss your presentation, you can stay online and we'll continue. I'll stop the recording now.